Hey guys, it's Christian, and today I'm going to be teaching you how to solve a system of equations using Gaussian elimination. So, what is Gaussian elimination? Gaussian elimination is just a way to solve a system of equations. You already know probably about substitution and elimination. Well, Gaussian elimination just draws upon both of those to solve a system of equations. So there's two ways you can do Gaussian elimination. You can either do it with a matrix or without a matrix. And the first example we're going to look at, we're going to solve it without using a matrix. The whole point of Gaussian elimination is to set up the system of equations so that it is in order, so all of the variables, it doesn't matter which one is first, but y is all here, for example, x is all here, z is all here, and the constants are all over here. And then once you have that, to make the leading coefficient to each variable to be 1. So as you can see with this set, this isn't in order yet. So the first thing we're going to do is put everything in the same order. And that could be whatever you like. But for me, I'm going to set it so it's x first, then y, then z, then the constant. So first, we can just start off by rewriting this equation to flip around the x and the 3y. And then it looks like our second equation is already in the order that we want it. And for the last equation, we just need to get the 3 and the 3z flipped around. So we would subtract the 3z over here and add the 3 over here. So after that, you would get minus 3z on the left side and a positive 3 on the right side. Perfect. So now you want, as I was saying about each leading coefficient being 1, you want it at the top for the first one to be 1, down here for the x to be gone and the leading coefficient on the y to be 1, and then down here x and y to be gone, and then z to have a leading coefficient of 1. And now there's no right or wrong way to do this. There are several ways that you can get to that final outcome. It's just what looks the best, or what you think would be the best way to get those coefficients isolated like that. So on the first row, we're already good. We already have our 1x out front. We just need to figure out how to get y to have a leading coefficient of 1 here, and z to have a leading coefficient of 1 here. So let's think. As I was saying, there's not a wrong way to solve this as long as you multiply, add, subtract correctly, as long as you end up with the leading coefficients of 1 down the ladder. So here, to get x, to get the x eliminated from row 2, you can either subtract some multiple of row 1 from it, so that the x's cancel, or some multiple of row 3 from it. If we do it from row 3 though, you're going to have to deal with a fraction, which if you want to, that's great, totally up to you, but I'm just going to do row 2 minus 3 times row 1 and put that back in row 2 to get the y without the x in front. And since the y already has a leading coefficient of 1, we don't have to worry about that in this problem. So that would get us 3x plus y minus 2z equals 7 minus 3x minus 9y minus 6z equals negative 15. So when you do that math down the row, you'll get negative 8y minus 8z equals negative 8. So actually take back what I said about the leading coefficient in front of the y, because now we have the x eliminated, but the coefficient is no longer what we want it to be on the y. Thankfully, the way this problem works out, we have a greatest common factor here that could get the y to have a leading coefficient of a 1. So we could take negative 1/2 out of row 2, and apply that to row 2. And we're allowed to do that because we're applying the negative 1/8, because we're applying the negative 1/8 to both sides of the equation. We can multiply both sides of this equation by 1,000,000 if we wanted to, and that's okay as long as we do it to both here and to here. So after we do that, you're going to get in row 2 y plus z equals 1. Perfect. So that's what we want in row 2 with a leading coefficient on the y. And yeah. Alright, so to save the time, I just plugged that new row 2 that we just got back into there. And now the only thing left to solve the system by Gaussian elimination is to deal with the last row. So how could we get rid of the x and the y and then get the z by itself? So I think it's best here to focus on just one thing at a time. Let's start by eliminating the x. So we can do that by having row 3 minus 2 times row 1 and plug that back into row 3 and see what we're left with. So that would give us 2x plus 2y minus 3z minus 2x minus 6y minus 6z equals minus 4z equals negative 10. And then once you math that out, you get negative 4y minus 7z equals negative 7. Alright, that's a good start. Not quite what we want yet, but we've gotten the x out of there, which is good. Now, to get the y out of there, we can look maybe just at row 2 and multiply row 2 by 4 and add it to row 3 to get the y canceled out. So we'll do row 3, our new row 3 that we got down here, plus 4 times the row 2 that we got and plug that back into row 3. So that would get us negative 4y minus 7z equals 7 plus 4y plus 4z equals 4. And then when you math that all out, you'll get negative 3z equals negative 3. Alright, so cool. Now we just have the z. Even though it's not a coefficient of 1, this looks good because now all we need to do, like we did to row 2 after getting the 8s with the y, multiply it by negative 1/3 to row 3, and then put that back in row 3. And then that'll just get you z equals 1. So for our final system, we can eliminate this now, and instead put back into there z equals 1. And then this looks like how we want our system to look in a Gaussian elimination problem. So even though it was a little bit of a hassle initially to get that Gaussian system of equations set up, now that we have it set up, it's very easy to solve. I like to think of it as kind of working up the ladder. So you have z is equal to 1, so you're like, okay, now up here to find y, you just do y plus 1 equals 1. And that just gets you y equals 0. And then, now that you have z and y, you have x plus 3 times 0 plus 2 times 1 equals 5. And you get x plus 2 equals 5, x equals 3. And there you go. That's that example without a matrix worked out. Gaussian elimination problems can also be set up using a matrix. So let's solve this example problem setting it up as a matrix instead. So this you can rewrite as 1, negative 1, negative 1, put a dashed line to delineate kind of like the separation between like the equal sign. Then you have on the other side is 7, then -1, 2, -3, -12, 3, -2, 7, and 30. Excuse me if that's a little off center. I have a limited visibility, but now that you have this, you would apply the same row operations that you saw in the last problem, just set up in a matrix to simplify a little bit. So the first thing that I'm going to do here, normally you would want to start off with a leading coefficient, but I see something that I like down here because I know that I'm going to have to get a 1 down here, meaning this and this are going to have to be 0. And if I add this row down here, I can get rid of that second term. So let's try row 3 plus row 2 and plug that back into row 3. So that would get us, you can visualize the numbers here, and since it's simple addition, I'm not going to rewrite it, but you would have 2, 0, 4, 18. That would be your new row 3. Alright, I plugged in our new third row, so now let's take a look at the best next course of action. So, I like what we have going on here with the 1s. Those look like they can cancel out each other pretty well, and we need that for row 2. So, let's do row 1 plus row 2 and plug that back into row 2. So that would give us a 0, 1, -4, and -5. I have our new row 2 in there, but I just realized it was a little pointless to get rid of that second digit because it's going to come back when we try to get rid of the first one. But let's start by simplifying row 3 by multiplying the whole thing by 1/2 and put that back into row 3, and that'll give us 1, 0, 2, 9. So I've moved our new row 3 into its place, and now we need to figure out how to get rid of the 1 here, which, as much as it pains me, we're probably going to have to subtract row 1 from row 3, which would introduce the second digit back into the problem, but that's okay, we'll take care of that later. So row 3 minus row 1, putting that back into row 3, and that gives us 0, +1, +3, and 2. Okay, so I've plugged our new row 3 back into row 3. It actually doesn't look like it'll be too terrible to get that y, or second digit, back out. We'll just have to do like row 3 minus row 2, plug that back into row 3. And that'll give us 0, 0, -1, or no, excuse me, +7. And then on the other side, another +7. Alright, so that is great. We have our second digit out, and we just have our third and the 1 on that side, and they both have a greatest common factor as well. So that makes it really easy to get this 7 back down to a 1. Now we can just do 1/7 of row 3, plug that back into row 3, and that'll give us 0, 0, 1, 1. Okay, so now we can have our final matrix with our Gaussian setup. And there you have it. Alright, so now that we've done the setup It's pretty much smooth sailing from here. This is the easy part. We already know the matrix order lines up with the order we have up there. So the z is our bottom one, and if one coefficient of 1 on z equals 1, that's just z equals 1. And like we did last time, just work our way up the ladder. That we have y in the second row, so that just 1 on y minus 4z equals negative 5, or y minus 4 equals negative 5, and y equals negative 1. And last but not least, we have x in our first position, x minus y, or just plus 1, minus z, or minus 1, equals 7. And you just have x equals 7, because the ones cancel each other out. And there you have it. There's that matrix solved. And now you know how to solve a a system of equations with Gaussian elimination using both a matrix and not a matrix. All right, see you guys.